Yeah, okay, so I'm Jimmy Rader, for those who don't know me. And I'm introducing Bashi today because Bashi was my student and I was working in my group. So Bashi came to UNH in 2012 and became a graduate student here. And then soon thereafter joined my group as a graduate student. And she finally got her, not finally, she got, I mean, quite in time, I would say, her PhD in 2017, doing some simulations of Earth magnetosphere, focusing on how signals propagate through the magnetosphere. During that time, she actually was also invited on two so-called ISTI teams. I mean, that's the International Space Science Institute in Bern, Switzerland. So that was back in the time when one would actually travel to Switzerland and have a good time there for a week and talk about issues. And so she was invited as a young scientist. They usually are small groups of about a dozen people, and they can invite one or two young scientists. And Bashi was one of them on both of these ISTI teams. Another success story was that she wrote a paper, the first paper she wrote, actually had a figure that the editor liked from JGR. So the editor put that on the front page. So that's also quite an honor if you can have your article advertised that way. So eventually, Bashi graduated in 2017 and looked for another job and found one, technically at UCLA, but she never moved to California because she was really working here at Boston University. I mean, with Toshi Nishimura's group. So she did that for about a couple of years. I think wrote one or two papers during that time. And eventually, about a year and a half ago, I mean, she came back to UNH. So has been working in my group on various topics, actually. So Bashi has wide area of interests, you know. So that was part of it was coupling of the magnetotail to the aurora. Another one is so-called SAPs, suborbital polarization streams, which you'll be talking about today. And she also won very quickly a grant from the Living with a Star program, which is on yet another topic. I mean, ground-induced current. So that program is just starting, and will help her pay her salary for the next 4 years. And on top of that, she is also co-I on a grant where Amy Kesey is the PI, which was also funded recently. I mean, at least unofficially so far. And so she has been quite successful. And I think I'll leave it at that and ask Bashi to give us a presentation. Thank you.
Thank you so much, Jimmy, for the nice introduction. And so I'm going to start. So everyone sees my slides now.
Yep, we can see the slides and hear you just fine.
Perfect. So as Jimmy said, I'm really interested to do like different topics, and so that's why my subject title was very like broad: magnetosphere, ionosphere, thermosphere, and coupling phenomena. Okay. So sun constant. So I'm for my talk, I'm going to go a little bit into introduction, and because we have students here, so I'm going all the way to the sun. Sun constantly disputes these high energy particles towards outside, and our magnetosphere is supposed to protect us from all these hazards. However, like any system in universe is not a perfect system, and these particles could penetrate our system. And most of the time, they show themselves as beautiful auroras, and particle accelerate along these field lines towards the ionosphere. But sometimes these can be hazardous for our infrastructures, like our power grids, pipelines, and railways. This is a new challenge, is geomagnetically induced current. Challenge, I mean, like when we became dependent on technologies, because in the past there was no power grids, and we were not affected with these coronal mass ejections. So for my talk, I'm going to start from the ground. I'm going to talk about geomagnetically induced currents, and then I'm going to move a little bit higher in altitude and go to 400 to 800, talk about subauroral polarization streams or SAPs. And again, I'm going to move a little bit higher in latitude this time, and I'm going to talk about auroral features like polar band intensification and streamers. And we're going to see how these are foot points of bursty bulk flows in the magnetotail. So this part of the GIC that I'm going to show you was done during the FDL, Frontier Development Lab, during the past summer 2020. So Frontier Development Lab is a partnership between NASA and private companies like Google, NVIDIA, and they try to bring people from a research domain and with machine learning background and combine them, and they work on critical subjects that could have big hazards in humanity. Like GICs was one of those effects. So what are GICs? GICs are geomagnetically induced currents that, as I said earlier, that could impose critical hazard for our infrastructures like power grids, telecommunication system, railways, and pipelines, because all of these infrastructures are made of metal, so they could act as a circuit with the ground. And our biggest challenge is actually is that GIC data is not available. Because the power companies do not share these sort of data with us. But on the other hand, the good news is that GICs are driven by geoelectric field that through the Ohm's law depends on Earth conductivity, as well as through the Faraday's law through ground magnetic field perturbation. And from measurements from ground magnetometers, this is the stations of the supermag all over the globe, we're able to determine ground magnetic field perturbation, either dB, and from that we could get dB dt that leads to GIC. Again, you see the challenge is that even with the ground magnetometer data, we don't have a full coverage. Look at Russia, for example. We don't have much measurements here, or Southern Hemisphere. So how can we know GICs or predict dB dt all over the globe? One of the methods is just we create a model that we can have determine dB and dB dt all over the globe, like either by MHD models, self-consistent modeling that we already have in-house at UNH. And also we could use new techniques, machine learning, to create dB dt all over the globe. So our goal our goal is to create a model to predict magnetic field perturbation. And our model has two parts: a global reconstruction model and forecasting model. For global estimation of dB, we use spherical harmonic decomposition. And for forecasting model, we apply deep learning on top of this spherical harmonic to predict the coefficients of spherical harmonic, which translates to ground magnetic field perturbation. So let's first talk about the reconstructed model. For this part, we use data from the supermag, mostly above 40 degrees latitude, because as you can see here, we have better coverage here than Southern Hemisphere. And this is for the reconstruction. We only use 1 day of the data with 10 minutes time cadence. In addition, what was unique about our work was we used MHD simulation model as a ground truth, because these models will capture the large scale perturbation, and we can see what happens if we have a full coverage of ground magnetic field perturbation. So To create the model, we use spherical harmonic fitting using lasso regression to obtain sparse representation of global dB. Basically, we need to determine the hyperparameters. We are looking for L1 should be L1 should be minimized, and then alpha should be minimized, and L1 should be maximized. So if you look at this heat map, we're looking for the regions that there is a sharp gradient in the color. For example, look here from orange to yellow. That corresponds to alpha maximum number of 20, and the alpha 0.1 minimizes the alpha. And the same is in R2 maximum over time, the region from yellow to white. So this is how we created the model. The next step was to validate our model. To validate our model, we used MHD model simulation. On the left, you see the ground truth MHD. In the middle, we extracted delta B at the supermag locations. And finally, on the right, we applied a reconstructant and determined delta B from MHD. That way, we are able to see how these compare to the ground truth. As you can see, there is a good consistency between these two plots. You see these, we are able to capture these intensification, red and below. We are missing a little bit of part of like a small parts, but in general, our model that with alpha 20 number of modes and alpha 0.1 does a pretty good job here. So of course, the next step to compare with the state-of-the-art Weimar model. On the left, you see the reconstructed model, and in the middle, you see the supermag, and on the right, you see the Weimar model. So I want to take your attention to, for example, this chain. This is a Greenland chain, and it's from measurements from the supermag. You see all these red areas, and look at our model, reconstructed model, these red areas here, and then a little bit of blue. And let's look at the Weimar. Weimar is not as not well capturing these things. And also look at these, another cluster of magnetometers here in northern part. And we are able to capture in our model, not as much in the Weimar model. So basically we were able to reconstruct dB, and this is dB, dB based on spherical harmonic. So the next step is to apply the forecasting model on top of that. For this model, we use similar setup as Weimar model, and shown in the table, you could see what parameters that we use. We use IMF parameters, plasma velocity and temperature, clock angle, as well as F10.7, and that's for 1 year of data during 2013. The input solar wind data is in 20 minutes vector with 20-minute lag to forecast and 5 minutes averaging as target. So here is our model architecture, where we feed 25 minutes of solar wind activity into gated recurrent network to map the sequence into an embedding vector. We then feed the embedding into multi-layer perceptron, or MLP, to output the spherical harmonic coefficients. That, as I said, translate to magnetic field perturbation. For this part, we only focus on north component of dB as a proof of concept just for now. Then this is our result. On the left, you see the prediction based on the spherical harmonic, and in the bottom, you see the supermag location. And if you look at, like, for example, look at this time. You see our model forecasting model is able to capture most of the length scale, and especially at the location of the supermag. So So the next step to validate model more, we benchmark this work against, again, the state-of-the-art empirical model by Weimer. To evaluate the performance, we first compare on the validation set on SuperMag, but also compare on simulation conduct with MHD model for 2 weeks worth of activity. We showed that by using deep neural network to forecast in the spherical harmonic space, we can improve the existing state-of-the-art Weimer model by 14% on SuperMag and 24% on MHD. So here is the remarks of GIC. So I'm going to spend the 10 minutes for each topic, and then I'm going to move to the next topic. So here are the our remarks. We developed a global geomagnetic perturbation model using lasso regression. The composition of MHD simulation demonstrates potential for data comparison using compressed sensing techniques. And GRE and MLP forecasting shows improvement of 15% over SuperMag and 24% over MHD model. So the future plan, as Jimmy said, I got recently a NASA Living Good Star Award. And for that part, I'm going to focus on like modeling GIC from the solar wind to the ground. Basically, I'm going to study how GIC behave under geomagnetic conditions, like do GIC driven under CME different from CIR or substorms, and which currents are responsible for driving GIC. And for the FDL part, we are preparing manuscript, and we're going to validate our model with Ampere because they have better coverage over the polar cap. So let's move a little bit higher in altitude and talk about SAPs. So I think the SAPs started was promoted and introduced mostly by our neighbors down in MIT Haystack Observatory in I think early 2004, and because they were the perfect latitude to see this phenomenon in their incoherent scatter radar. And they were able to perform many statistical studies about SAPs. And so that's how it became very popular, I think. So what are the SAPs? SAPs are identified as intense northward electric field, as you see here in this top picture. And they're formed as the interaction between region 2 field line current and low conductivity region that we have below precipitation. And they can then accelerate ions towards the sun. So that would be duskward on the, westward in the dusk and eastward in the dawn. So this is from super dawn measurements. So basically SAPs are separated from our two cell convections, and they are in the low conductivity region. And they usually happen during geomagnetic active time, like storms. So what was the motivation that I started doing this? Because before this study by Zhang in 2015, he's part of MIT Haystack Observatory as well. So people would only see SAPs as the combination of magnetosphere ionosphere coupling process. But what he noticed that these are the measurement from incoherent scatter radar. So these are the SAPs that you see at time 20 UT. And what they noticed that on the neutral wind have been accelerated with these SAPs with like 1 to 2 hours time delay. And so these are about poleward winds, and we wanted to see what happens to the westward winds. Also, they suggest that these are formed as due to the Coriolis force, and we wanted to see what forces actually drive westward winds. So for that, during my postdoc at BU, I used DMSP and GOCHI data. For DMSP, it's at 800 kilometer. It provides measurements of plasma density, precipitation, electron, and ion velocity. And GOCHI is at lower altitude and provides measurement of neutral winds and cross-track velocity. We did this this time because, as you see, this blue is GOCHI and then pink is DMSP. They have a good, like, overlap at 18 and 20 MLT. In addition, we use the couple simulation model, CTB RCM. This is one part of OpenGGCM as well. We have CTM instead, so it doesn't have the MHD part. For the higher precipitation, it uses the Tyrus model, and for the lower latitude, it uses the RCM precipitation. The advantage of these models is that they self-consistent couple. They provide self-consistent coupling of magnetosphere, ionosphere, and thermosphere. So this is the observation for the 2013 St. Patrick's storm. On the top, you see the BZ conditions is pretty negative for this storm. And you see the SIM-H. SIM-H shows when the storm happens. For example, this is storm starts from, this is the the first tip of the storm at 8:30 and then at 11:30. And usually SAPs happen during this time. And on the other plots, there are energy flux, field alone currents, Pedersen conductance, ion density, velocity. So when we're looking for the SAPs, we usually look at the ion velocity. Look at here. These are the SAPs. They are below auroral oval. They are within the trough. There's density is low on that area. And another thing is that we see in the GOCHI, the last panel is the GOCHI, we see the wind shows similar behavior of the SAPs, but with 2 hours time delay. So we wanted to examine what forces are driving these neutral winds and how much these neutral winds can feed back the ionosphere. So basically the effect of thermosphere on the SAPs. So when we do simulation, always the first step is to validate our model to see if our model, for example, for that particular event can create the same behavior as observation. So this is the same parameters as you saw in previous plot. I'm just going to show how they behave like in a line plot. This is ion velocity. The red is the DMSP, and the blue is the simulation during the storm St. Patrick's 2013, and the black is the simulation during the quiet time. And in general, we put this like during the, because DMSP goes through the orbit, so we have like certain time that we have data on the dust. So we put the dates like a virtual satellite in our simulation to see how our simulation compares with the observation. As you can see here, in general, our simulation is able to reproduce over a structure of the SAPs and neutral wind. So the next step is to study how different forces drive the neutral wind, as we were talking about. So this is the neutral equation of the motion. We have different forces. We have ion drag and Coriolis force, horizontal advection, pressure gradient, and viscosity. And we will, and as you can see it here, each of these forces correspond, each of these panels correspond to different forces. And up here you see the simulation of the ion velocity, and then neutral velocity. So we notice the ion drag in this panic is the most dominant force driving the neutrals. And after that is a little bit Coriolis force, especially during the second dip of the storm here. And the horizontal advection has some effect at the lower latitude, and pressure gradient only has a minor effect on driving the westward neutral winds. This study was interesting because when we talk about SAPs, SAPs are formed during the trough, where the density is lower there. So people would think, so because density is low, so the ion drag, which heavily depends on the density, cannot drive the neutrals. So that should be Coriolis force that drives them. And so we realized that because the difference velocity between the ions and neutrals was very high, so basically neutrals were sitting there and ions were dragging them along the ion drift. So that's why this happened. And finally, we wanted to see how neutral wind affects the SAPs. So on the left, you see the plot for the field along currents. And on the right, you see the plot about the westward ion drift at the dusk region. We realized that we created two simulation runs, one with neutral wind, and for the second one, we turn off the wind. So with the simulation, we have a luxury to become God, because we can turn off one parameters and see what happens. And we realize when the wind feedback is available, the region 2 field line current is enhanced, and total field line current increases by 20%. And as a result, the ion drift extends to lower latitude here, as you see here, and enhances SAPs by 30 to 40%. So the neutral wind amplifies MIT coupling process, and that is mostly known as flywheel effect. So that was during my postdoc at BU, and then I continue to do the SAPs at UNH using the simulation of OpenGGCM RCMC team. And you see that this is the same event, St. Patrick 2013. And you see these features below auroral oval. These are the SAPs. They are separated from the main convection cells, and they are within the region 2 field line currents. But I did further investigation, and our model reproduced SAPs as like as lower latitude than observation, but we're figuring this out later. And the next step with the UNH part, OpenGGCM part, I wanted to see what parameters, the most important parameters, for example, region 2 field line current. And another important parameter is recombination rate and precipitation, electron precipitation. How can these affect the SAPs? And what I've done, I created reference run, and that is on the top here. And then I had the run with no RCM. So basically with no RCM means that region 2 field line current dies. And then I have a run that I set the recombination rate to 0, and another run that decreased the precipitation by half. As you see, if you compare with the reference with the no RCM, basically, and this is the time that during the storm, and I want to see how these exactly behave. So as you see, the SAP's strength increases when the precipitation decreases to half, and actually increases when we decrease the precipitation. And when the recombination recombination rate is 0, the SAP is very weak. And when there is no RCM, basically there is no SAPs. it's probably some other features. So also I did like, the line plots at MLT 17. This is the blue is the reference run, the green is when the recombination rate is 0, and the red is the difference between them. And we realized that Sap's strength increases by 60% when the recombination rate is 0. And when we change the precipitation to half, the Saps actually enhanced by 40%. So the remarks of the Sapsa neutral wind, the ion drag dominantly accelerates the neutrals. The neutral wind exhibit the flywheel effect equatorward of the Saps. Basically, after there is no driver for the Saps, neutrals can drive Saps onto their direction. And wind has positive feedbacks on the MIT coupling process. Also, region 2 field line current, as was mentioned, is the main driver of SAPs. When we killed the RCM region 2 field line current, SAPs completely disappeared. And recombination rate and precipitation also has strong effects on SAPs formation. So the next step, this was part of the Jimmy's NASA Living with Star grant that's from 2017, and it's going to have, like, we're going to have for, I think, 2 more years with the extended. So we wanted to see how the SAPs and SED and TOR depends on different solar wind drivers. And we're gonna perform large number of runs to serve parameters like how different solar wind parameters could affect these phenomena. Also, another thing that has been recently interesting, that people are seeing SAPs, but they're not sometimes calling it SAPs during quiet times. And recent study by Konduri showed that there are some enhancement in flow velocity in the mid-latitude region. So we're studying those as well. And another thing is that we always have like these enhancement in the dusk, but we do not have the strong enhancement as dusk in the dawn. We wanted to see what happens in the dawn. For example, DAPS. Are there forces that killing these ion velocities? So are there things like, for example, ion drag or Coriolis force acting against these ion velocity that decreases these eastward intensifications? So the next step is Bursty bulk flows and roller streamers. So this is the subject I'm really interested to, because our in situ measurements in the magnetotail is very limited, and they're like, if we have it, even though with the TMS or MMS, we have it at just a couple of points. On the other hand, in the ionosphere, we have broad range of measurements, like all sky imagers, radars, and then imagers from outside. And at some point, to some scale, ionosphere acts as the projection of the magnetotail activity. So if we understand how these roller streamers correspond to Bursty bulk flows, we might be able to remote sense the magnetotail activities. So let's start from the beginning. What are Bursty bulk flows? BBFs are short-lived high-speed plasma interrupted as plasma bubbles. And they are very important because they're responsible for transfer of 60 to 100% of energy, mass, and magnetic flux to the ionosphere. So what happens as these bubbles move, there is a shear around them. And then as a result of this shearing, vorticity happens around them. And as a result of this vorticity, field line currents form around them that connects them to the ionosphere. these are similar, their polarity is similar to substorm current wedge, but it's very much smaller scale than the substorm current wedge. But you know, these are they are how these are connected to the ionosphere. So what are those signatures that you saw in the tail? In the ionosphere, they are either in the form of PBIs, which are intense and transient auroral disturbance, and they initiate around the magnetic separatics, and they are formed streamers when they extend equatorward in the auroral oval. As you see, this is the data from image, and these are basically streamers and PBIs. So why do we need, so there's a bunch of studies that already done that. Why do we need physics-based model to study these relation? Because previously, for example, the study by Zesta et al., they used the mapping from the ionosphere to the magnetotail based on the Signanka model. The challenge with the Signanka model is that they're not reliable on highly stretched configuration because they do averaging of the magnetic field. So for example, during the strong magnetosphere, you know, when the tail is very stretched during this substorm, they might not represent the accurate estimation of the magnetic field. So we wanted a physics-based self-consistent model that could do this mapping. So that's why we use OpenGGCM, RCM, city model that achieve this goal. So to study this is the same events as Zesta et al. Study. It's during the substorm 3-2001, and it's an old substorm, but we had so much measurements and we had good observation that we could compare our simulation with that. So on the top, you see the AE index, which is an AE index shows it's one of the indicator of the substorm. I'm not gonna show this everywhere because like some people are skeptical about AE index. So everyone has their own, but one of the scales that like I think Vasilis also used was AE index. And here is the IMF conditions. IMF PZ is pretty southward for this event, and IMF BY is interesting because it starts from a little bit negative and then becomes 0 and goes to positive. And so I started the simulation 5 hours prior to substorm onset, which was 2:30 UT in the observation. And at 2, I see these intensification. At the beginning, I thought these are the substorm, but then I realized that so this is the kilogram based on the simulation at MLT 23, pre-midnight, midnight, and post-midnight. So I realized during this enhancement in the aurora, there is no substorm, there is no westward traveling surge or auroral expansion. Whereas at 2:30 during this enhancement, during this breakup, you see there is this equatorward movement, there is this westward traveling surge. So we identify, and also during this time, AE index is increasing and reaches to 200 nanotesla. And this is one of the events, and this is one of the characteristics that Angelopoulos used to identify the substorm. So we say the substorm happens at 2:30 because it has the typical signature of the substorm that was introduced by Akusafo and then Angelopoulos. The next step is, like, as I said, we always have to see how is our model performing in comparison to observation. We wanted to see what are the signatures of BBFs in the magnetotail. On the left, you see the statistical study based on Ohtani et al., and that are the typical signature of the BBFs. There is the increase in the velocity, there is a depolarization front, there is reduction in density and temperature. And this on the right, you see the satellites, virtual satellite in the OpenGGCM at x minus 20 and y minus 5 in the plasma sheet. On the top, you see the Vy. There is an increase in the velocity associated with depolarization at BZ, reduction in density and pressure. So this is just for one of the BBFs, but I examined number of BBFs and they show similar behaviors. So our simulation was able to produce BBFs consistent with observation signatures. The next step was to see how these BBFs map to the ionosphere. So why do we do this mapping? Because the model grid cannot sufficiently resolve the aurora's fine structure near the ionosphere, because the field lines converge in scales that were 5 RE in the magnetotail becomes very narrow in the ionosphere, and ionosphere cannot resolve them numerically. So that's why we did the mapping. For the mapping, you see in the movie, these are earthward velocity, and we map them along the magnetic field line to the ionosphere. We basically wanted to see, for example, you see these BBFs, these like big BBFs, how this behaves in the ionosphere. And after that, I went manually choose 47 of BBFs and streamers and wanted to study how these BBFs compare to the auroral streamers. And so this is the plot for the ratio between auroral feature area with BBF dimension. As you see, they are correlated with the streamer size is correlated with the square root of BBFs, and that's basically the size of the flux tubes. And this is not always the case because these flux tubes sometimes gets distorted and is not always valid, but in general, this is how it is. And next step, I wanted to see how the location of BBFs and streamers change during different state of the magnetosphere. For example, on the blue is right before the substorm onset that I showed you. And the green is like 30 minutes just during the onset, and the magenta is during the steady magnetic convection. During this event, if I go back, so during this event, the IMF-BZ was negative for a long time. Basically, when IMF-BZ becomes negative and continues to be negative, the reconnection on the night side becomes balanced by the reconnection on the day side. And the magnetosphere goes into the state that is called steady magnetic convection. And also another signature is that the AE index stays pretty constant during this time. So I separated different parts before the substorm onset, during the onset, and after 3:30 during the steady magnetic convection. And based on that, and each plot correspond, for example, the top 4 are the BBF's location in X and Y, BBF length, BBF width, and during different state of the magnetosphere. On the bottom, we have the same for the streamers on the ionosphere. And we see that, for example, the location and then the location of the BBFs, especially in X direction, depends on the state of magnetosphere. And also another thing is that during this time was interesting because before the onset, IMF-BY was negative, and and during the substorm onset, IMF-BY became 0, and during the SMC, IMF-BY became larger than 0. So that's another thing similar happen. That another simultaneous thing, but the state of the magnetosphere was this, and we realized that during the BY0, the BBFs are in the dusk, and during the BY0, BY larger, sorry, oh, sorry, BY. They would be mostly in the dawn when BY becomes positive, and they're in the midnight when BY is 0. And another thing is the lengths of these BBFs do not depend on the state of magnetosphere or the IMF BY, but their width changes. For example, during the pre-onset, they are like wider, whereas during the SMC and onset, other time, they're narrower. And another interesting thing was like, yeah, there are all, for example, if you look at BBFs in the tail and the ionosphere, they almost show the same behavior. If you don't see like, those behaviors, that's because of the configuration of the magnetosphere and the tilt of the Earth. So the remarks for this study is that this study provides an opportunity for remote sensing of the magnetotail activity. And I didn't show here, but we realized that BBF do not always move in the straight line. And they mix and merge as they move earthward, leading to streamers in the ionosphere. That's how the streamers are moving too. The number of flow channels and their strength in the plasma sheet increases during the substorm expansion and again during the SMC interval. And the same with the auroral activity. And we realized during the SMC, flows penetrate closer to the Earth. And at the same point, multiple fast flows can be available in the tail with different reconnection sites. So the next step is Amy has a new grant, as Jimmy said. We're going to study the relation between understanding magnetic tail activity with ionosphere through imaging. I'm going to do the simulation part. Also, I'm thinking about a machine learning project, how to improve OpenGGCM with machine learning. For example, you saw that we are able to get the substorm, but sometimes we're not able to get substorm all the time. We want to have like a model, we want to have a method that tests the different parameters and comes up with the best model to produce the substorms. And hopefully we're going to survey BBFs characteristic in the tail with machine learning and using OpenGGCM, Themis, and Cluster in the tail. And based on that, we hopefully create a database for magnetosphere ionosphere response to the tail activity. And at the end, so these are the summary. We developed a global forecasting model to predict ground magnetic field perturbation using spherical machine learning on a spherical harmonic. We realized that thermosphere has a contribution on SAPS formation through the neutral ring. Also, region 2 is the main driver of the SAPS, and recombination rate and precipitation affect SAPS strength. Those were based on numerical experiments. Also, at the end, MHD simulation successfully produced PBIs and streamers, and IMF BY and state of the magnetosphere affect orientation and strength of the BBFs. And that's it. Thank you.
Thanks, Vashi. Sorry, I don't know if Jimmy wanted to open it up for questions here, but excellent talk.
I think that's your job, Kevin.
Okay. I could only abide the silence for so long here. Yeah, I hope you're seeing the little applause emojis all coming from the participants list here, Vashi. If anyone has any questions here, feel free to jump in.
Yeah, I noticed you mentioned using the Weimer model to compare against your DBDT model from neural networks. I was wondering if having a better electric field model would influence. I suppose you already have your own model, but if you had a better empirical electric field model, how would you make use of it?
We were thinking about actually to use instead of going to the models, we stick with this model that we have. Instead, we go different data sets, like for example, Ampere data set, and see how our reconstruction performs on those, those data set. But in general, I think, those we realize with the Weimer model, there is not much validation has been done. But the good thing about the Weimer was he used the parameters that basically helps our machine learning to learn faster. So that's why we used his parameters.
Okay. And do you think I guess the drawbacks of his model affect your model in an adverse way?
So I'm not sure. When we applied his, the only thing from his model that we used, it was the solar wind parameters. Like for example, instead of giving using f10.7, for example, using clock angle, those sort of things that we gave it to the model, so model learns faster. But other things were completely different from the Weimer. And we started doing our own, feeding the solar wind to the model. It was not going as good as when we fit the same as, Weimer.
Okay, thank you.
Sure.
Anyone else? Going once. Well, clearly, I think you explained everything perfectly, Bashi. So okay, Eric Lund says, nice talk, first of all. He has to go, but he would like to hear more about your PBI results.
Yeah, it's under review, so hopefully it will be published soon, but I can definitely forward you the manuscript before, right now.
Great. Well, if no one else here wants to come off mute, ask a question to our speaker, then I think we can wrap up 5 minutes early. So thanks again, Bashi. Really nice talk.
Thank you.
And yeah,
sorry if
everyone.
I talk very fast.
No, I think that was perfect timing. All right, so have a good one.
Thank you.
Great job, Bashi.